everyone and welcome to Chapter 3, video number 3 in the three-phase induction machine course. Let me remind you that what we covered in video number 1 and video number 2. In video number 1 we covered the power flow diagram, and video number 2 we covered the torque speed characteristics or torque calculation. So in this video we are going to have two examples as an application for power and torque calculation. Let's start. Example number 1. A three-phase four-pole induction motor is connected to a 50 Hz supply and operates at a speed of 1440 RPM when supplying a load torque of 80 Nm. Please note the speed is 1440 RPM at a specific torque 80 Nm. So we need to calculate the mechanical output power, the rotor copper loss, and the total power input to the rotor. And we can neglect the mechanical loss. Before we start the problem, we need to call back the power flow diagram. So we have input power, we have a stator loss, we have air gap power, and rotor copper loss, developed power, and rotational and mechanical loss, and output power or net power. That one is neglected, so the mechanical loss is neglected. So the output power now is developed power. So we need to calculate the developed power and the rotor copper loss and power input to the rotor, which is the air gap power now. So let's see what is given. So three-phase induction motor, supply frequency is 50 Hz, number of poles is 4, and rotor speed at this torque is 1440 RPM and 80 Nm. From the given, we can calculate the synchronous speed, where the synchronous speed ns equals 120 fs over p equals 1500 RPM in this case. Also, we can calculate omega s, which equals 2 by ns over 60, 157.1 radian per second. We can use that one to calculate the air gap power, where B gap equals torque omega. So we have ns and we have nr, so we can calculate the slip. Slip equals ns minus nr over ns equals 0.04 in this case, or we can write it 4%. As the mechanical loss is neglected, so we can say that power developed equals power output equals torque developed multiplied by omega r. But what's omega r? So omega r equals 2 by nr over 60, which equals 150.8 radian per second in this case. So now P developed or P output equals 80 multiplied by 150.8 gives us 12.1 kilowatt. So still we need to calculate the rotor copper loss and the air gap power. So let's calculate the air gap power first. So the air gap power, or the total input power to the rotor circuit, will be B developed over 1 minus S. So we have the S and we have B developed, so we calculate that one, 12.6 kilowatt. Also, B gap equals torque omega S. So we can substitute in this equation 80 multiplied by 157.1 radian per second will give us the same answer. To calculate the rotor copper loss, we can use the equation SB gap. So we have S 0.04, we have B gap, so that one is 503 watts. Or we can have B gap minus B developed, which equals the same value. So the example here explains how to calculate the power in the rotor circuit using the power flow diagram. Example number 2. A three-phase 220 volt, 50 Hz, four-pole, delta connected induction motor has an induced rotor voltage frequency of 2.5 Hz at loading conditions and has the following parameters at standstill. R stator equals R rotor equals 1.2 ohm, X stator plus X rotor equals J6 ohm. So we need to calculate the slip, stator line current, input power factor. We need to plot the power flow diagram labeled by the power values if the rotational loss is 200 watts, and we need to calculate the motor shaft and the developed torque. So before we start the problem, I need to highlight here that the motor is delta connected. So this is why there is no information about the voltage. That one is line or phase value. So definitely that one is line voltage equals phase voltage in delta connection, 220 volts. So let us list the given. The motor is delta connected. V line equals V phase equals 220 volt. Supply frequency is 50 Hz. Number of poles is 4. The induced rotor voltage has a frequency FR equals 2.5 Hz. and this information, and this one will give us S. We have this R stator equals R rotor equals 1.2 ohm, and X stator plus X rotor equals J6. We can write X equivalent equals J6 ohm. Rotational loss is 200 watt. So let's start by part A. How to calculate the slip. So the slip can be calculated either using NS minus NR over NS, and we don't have any information about NR here. But we have information about FR, so we can use the equation that FR equals SFS. So S equals FR over FS. That one is 2.5 over 50, gives you 0.05 or 5%. For part B, we need to calculate the stator line current. To calculate the stator line current, we need to calculate the stator phase current. And we don't have any information here in this problem about the magnetizing branch, so we are going to use the second approximate equivalent circuit. So we have R stator plus R rotor and Jx equivalent, R rotor 1 minus S over S. Either you write this one by this way, or you can put R stator alone and you can put R rotor over S as a separate impedance. So to calculate the current, rotor current or stator current phase value, we need to calculate the total equivalent impedance. So the total equivalent impedance is R stator plus R rotor over S plus Jx equivalent. So the value for that one will be 25.9 angle 13.4 degrees. You can write it in rectangular form or polar form. I presume you know now how to convert between polar and rectangular and vice versa. So now we can calculate the current. We assume that the voltage is 220 volt angle 0 phase value, because that one is delta connected. Divide that one by the impedance. You got the current 8.5 ampere and angle minus 13.4 degrees. So that one is the phase current. Phase rotor current equals stator current, because we use a second approximate equivalent circuit. So I put for you the current in polar form and rectangular form as well to check by yourself. But that one is the phase current. We need the line current. So to have the line current, you need to multiply the magnitude by root 3 and shift the angle by minus 30 degrees. So the line current is 14.7 ampere and angle minus 43.4 degrees. What about the motor power factor? To calculate the power factor, cosine theta V minus theta I for phase values. So cosine phi equal cosine 13.4, where the voltage angle is 0. The phase current has an angle 13.4, so the power factor equals 0.973 lagging power factor. So please note that theta V and theta I are for phase voltage and phase current, not phase voltage and line current. So we need to plot the power flow diagram. And to plot the power flow diagram, we need to calculate input power, stator copper loss, air gap power, rotor copper loss, developed power, and net power. So we are going to start one by one. So the input power equals 3V phase I phase cosine phi. So I suggest for you, or I advise you now, to open the power flow diagram as a back screen and look for the formulas we are going to use. I'm going to use the formulas directly now. So 3V phase I phase cosine phi, 3 multiplied by 220, 8.5 multiplied by the power factor gives us 5.45 kilowatt. So that one is the input power. Stator copper loss definitely will be 3I square R. So we have I rotor equals I stator, so 3I phase square R stator. Phase value for the stator copper loss. So that one gives us 260 watt roughly. I changed the color between the results. That one will be the blue color, or the green one is useful power, and the blue color will be something like losses. For the air gap power, so that one will be 3I rotor square R rotor over S, or we can say that one power input minus stator copper loss. So if we use power input minus stator copper loss, that one will be 5.2 kilowatt roughly, but also we can use that one as 3I rotor square R rotor over S, give you the same value, almost the same value. So we need to continue in the power flow diagram. So for the rotor copper loss, 3i rotor square R rotor, that one will be something like 260 watt, and the same like the stator copper loss, because we don't have any magnetization branch, and I stator equals I rotor and R stator equals R rotor for this motor. Also, you can calculate it as SB gap. For the developed power, so that one could be B gap 1 minus S, or B gap minus rotor copper loss, or you can calculate it as 3I rotor square R rotor 1 minus S over S. R rotor or R stator, all of them are the same. Right? So that one will be 4.93 kilowatt in this case. For the net power, we need to subtract from the developed power the mechanical loss. So that one will be P net equals P developed minus rotational loss. So that one will be 4.73 watt. So now we can plot the power flow diagram. We have input power 5.45 kilowatt. We have a stator loss something around 260 watt. Air gap power around 5.2 kilowatt. Rotor copper loss around 260 watt. And developed power something like 4.93 kilowatt. A rotational loss 200 watt. And the output power in this case will be 4.73 kilowatt. Definitely you can calculate the motor efficiency in this case. So now we can calculate the motor torque. To calculate the motor torque, we need to calculate the motor speed. We have enough information to calculate the motor speed. NS equals 120 Fs over P, 1500 RPM. Also, we can calculate omega S, which equals 2 by NS over 60, 157.1 radian per second. For the rotor, NR equals NS 1 minus S. So the rotor speed is 1425 RPM, and omega R equals 2 by NR over 60, 149.23 radian per second. So now we can calculate the developed torque and shaft torque. So developed torque either be developed over omega R or B gap over omega S. Both equations will give you the same answer. So we have B developed and B gap from the previous slides for the power flow diagram. So for B developed equals 4.93 kilowatt, B gap equals 5.19 kilowatt, omega R equals 149.23 radian per second, omega S equals 157.1 radian per second. Both will give you the same answer, 33 Newton meter. Regarding the shaft torque, that one will be P net, P shaft, P useful over omega R. And that one is the shaft torque, useful torque, net torque. So P shaft or net power or output power is 4730.1 watt over 149.23 radian per second, gives you 31.7 Newton meter. The difference between developed torque and shaft torque is the torque lost due to friction, and you can calculate it as P lost or P mechanical, which equals 200 watt over omega R. That one is the difference between these two values. If you notice in video number 3, I gave you 2 examples. These examples cover the power flow diagram and torque calculation from the power flow diagram, but didn't speak about any point or torque points, something like starting, maximum, and so on. So what will I watch in video number 4? In video number 4, we are going to cover a comprehensive example on power and torque calculation, including all the torque points. See you in the next video.